Hi, today we're going to learn about the inverse function. So we've learned about what a function is, and an inverse, think about what the word inverse means. It means to do the opposite thing in the opposite order. So in the real world, we can think of one of our favorite songs, head, shoulders, knees, and toes. In this example, you go from the head down to the shoulders, down to the knees, down to the toes. So the inverse of that would be going from the toes up to the knees, up to the shoulders, up to the head. So notice you're doing the opposite thing in the opposite order. Another example is just changing languages. So going from English to French, the inverse of that would be doing French to English. Okay? A simple math example of an inverse is if you have the total cost, if you want to find the total cost, you would just multiply 10 times the number of t-shirts, assuming that the t-shirts each cost $10. So in this case, you know the number of t-shirts, and you put it into the function to find total cost. So number of t-shirts is independent, and the total cost is dependent. It depends on how many t-shirts you order. But what if you wanted to do the inverse? So the inverse of that is when you know the total cost, but you want to find how many t-shirts that would buy you. So you take total cost, and instead of multiplying, you do the inverse operation, which is division. Dividing by 10. So you do the opposite thing. So in this case, total cost is independent and the number of t-shirts is dependent. So the number of shirts depends on what your total cost is. So in inverse relationships, in inverse functions, the independent and the dependent variable switch. Okay, so our learning goal for today, you can see it right there. We're going to need to be able to go back and forth with domain and range and also graph functions and their inverses. So make sure you're really comfortable with those things by the end of this video. So the inverse of a function is the reverse of the original function. The independent and dependent variables switch roles. So you can see here that this is a simple example of the area of a circle. So here you have area equals pi r squared, where the area is dependent on the radius. So this is where you would know the radius and you would sub it into the equation and solve for area. Okay, so here the area is a function of the radius. But the inverse is when you would know the area, so that's independent, and you would use that area to find the radius. So the radius is dependent. So this is the inverse of the function above. Now radius is a function of area. So notice here how we found this. We just kept the variables where we were and rearranged and solved for r. So instead of taking pi r squared, you do a square root, so that's the opposite of squaring, and then divide by pi, which is the opposite of multiplying by pi. Characteristics that are always true about a function and its inverse. So this box is important because it represents just basic facts that you need to know about a function and its inverse. These kind of things can be asked in a communication question, but they're also applied to all of your regular homework questions. So if the point A, B is an element of a function, this means is an element of this fancy E, then the point BA is an element of the inverse relation. So what does that mean? Well, if we have 2, 1 as a point on the original function, then the inverse would have the point 1, 2 on that function. Okay? If your original function had 3, 5, then what would the inverse function have as an element? It would have 5, 3. Okay, what about if your original function had 0, 0? Well, then the inverse, you switch these, so it's still just 0, 0. Okay, so if you have a table of values of your original function, then you just switch the x values and the y values to get the table of values for your inverse relationship. If the inverse relation is a function, it is denoted by this notation. So it's the fancy little f, like we normally use for a function, with a little -1. And if you're doing it at x, then you would just put the at x after. So make sure that -1 is up high, it's a superscript. And this is only used if your inverse is actually a function, which we'll get into more in the next video. So think about it, your independence and dependence is switching. So it only makes sense that whatever the domain is of your original function, that's going to be the range of your inverse. And whatever the range is of your original function, that will be the domain of the inverse. So why, and this again could be a good communication question, why is this true? It's because the variables switch dependence. Okay, so anything that was xy now becomes yx. So anything that was independent now becomes dependent, and anything that was dependent becomes independent. Okay, here's something that's really important to understand. So the graph of the inverse is a reflection on the line y equals x. Okay, so that means that's this line here, y equals x. So take a second to make sure you draw that line, y equals x. Remember, that's just, where 0, 0, 1, 1, 2, 2, 3, 3, that's what y equals x looks like, a slope of 1, y-intercept is 0. And think about why it would be a reflection on this line, okay? So let's say the point -2, 4 was on the original function. Then the point 4 minus 2 would be on the inverse function. And you can plot multiple points like that. And you can see that they're a direct reflection across this y equals x axis. Okay? But when would a function intersect with its inverse? Well, it's only on any points that would be on this line. And you might have already gotten that from above. Why is this true? Well, because AB on the function corresponds to BA on the inverse. So therefore, the only time when these are going to be the same, okay, this point is the same as this point, is if A actually equals B. So therefore, for AB to be equal to BA, then A has to actually equal B. Okay, or y has to equal x. So for example, the point 2, 2, if that's on the original function, then that's also an element of the inverse function, and that would be on this line. Okay, so there's some facts for you. Now we're going to actually put them into action and do some examples. Okay, so in today's lesson, we're only going to do inverse of linear relationships. Next lesson, we'll learn about quadratics. So to find the equation of the inverse, there's two different ways to do this. Number one, you can apply the opposite rules in the opposite order. Okay, and that's what we're going to do here for method one. And then the second way is to switch x and y and then solve for y. So in an equation like this, x and y don't really have any meaning. X is kind of just used to say, hey, I'm the independent variable, and y is just, hey, I'm the dependent variable. So if you want to actually find the inverse, you want to switch the dependence. So you want to put the independent variable here and the dependent variable here, but then you want the equation to be in the form y equals, so you rearrange. But you have to be careful for this. You only do that switching trick if they're in the form of x and y. If you have an equation like this, area equals pi r squared, you can't just switch area and radius. The reason being is because these two variables have actual meaning. This means area. It doesn't just mean the dependent variable. And this means radius. It just doesn't mean the independent variable. So in a case like this, you just keep the variables where they are and rearrange them to solve for the other variable. So you only do the switching if they're in this generic form of x and y. That's very important. Okay, so here we have this linear function, y equals 3x minus 1. So our first method is to say, let's do the opposite things in the opposite order. So notice that this one, it's saying you take your variable and you, so I'll write this down actually. So the original is saying multiply by 3 and then subtract 1. So the inverse, we run into these opposite things in the opposite order. So the inverse, instead of subtracting 1, we're going to add 1. Instead of multiplying by 3, we're going to divide by 3. Okay, so this is your function. So you have your variable, you add 1, and then you divide by 3. So that would be the inverse function. Okay, so that kind of just uses common sense and logic. This is the more like if you just want to learn an algorithm, then you can just switch the variables. So instead of y equals 3x minus 1, we're going to do x equals 3y minus 1. So we've just switched the variables, switched the dependents, okay? But we want to put it in the form y equals. So first we move the 1 over. And now we have to divide everything by 3. So there you go. It's the same equation, whether you do it this way or this way, but it is nice to write it just to have the y on this side as your final answer. So there you go. Those are the two different ways you can rearrange a linear function to define its inverse function. So remember, if you wanted to graph what these would look like, either you could just graph the lines using y equals mx plus b, or you could do a table of values of this linear equation, plot them, and then do a table of values of the inverse by just switching all the x's and y's and then plotting those and labeling that graph. So here we go. This is something that's a little bit more complicated only because it's not in y equals mx plus b form. So we want to find out what the actual function is in f at x form, and then what the inverse is in function form as well. So first, because we want it in function form, we have to write the original function in the form y equals. This represents f at x since y is dependent. So 5x minus 3y. So we just are trying to isolate y. So you move the 5x over, so it's negative 5x plus 12. And then to isolate y, you divide everything by negative 3. So negative 5 divided by negative 3 is just positive 5/3, and then minus 4. Okay? So here you go, that's your function. There you go, it's just a linear function with this slope and y-intercept. Okay, so to determine the inverse function, you just switch dependence. That's what I'm going to do. I'm just going to switch the x and the y around. So instead of y equals, we're going to have x equals 5/3 y minus 4. And now we just need to isolate y. How about you pause the video, try to do it on your own, and then check with my solution. So first you have to move the 4 over. Okay, so this is being divided, so you can look at this in two ways, okay? Either you can just say this is being multiplied by 5/3, so it needs to divide by 5/3, but fractions get complicated, so I would just do this in 2 steps. This one is being divided by 3, so this side needs to be multiplied by 3. And this is being multiplied by 5, so we need to divide by 5. And there you go. So now we're going to write it as a function. Okay, and you can distribute the 3/5 if you'd like. And there you go. That's your inverse function. Finally, we have this more realistic example, but it's still just a simple linear function. So if you want to find 20% of a number, one way is to find 10% of that number and then double that result. So find 10% and then just double it. So let the function f be the method for finding 20% as a number. So let's say let n represent the original number, and let's say let p represent what 20% of that number is. Okay, so our original function here, okay, so, sorry, that should be colon. So the 20% p would be equal to n divided by 10. That's how we find 10%. Okay, and then just multiplied by 2. We double it. So we divide by 10 and then multiply by 2. So the inverse would be to find the number, you take your percent and divide it by 2, and then multiply by 10. So instead of dividing by 10, then multiplying by 2, you're dividing by 2, then multiplying by 10, doing the opposite things in the opposite order. Okay? So when might this actually be useful? Well, let's say you have a number, and you want to know what 20% of that is. Oh, sorry, what that number is 20% of. Okay, so this one tells you, if you have a number, what is 20% of that number? And this one tells you, if you have a number, what is that 20% of? So that's how it might be useful. Okay, so that's our first lesson on inverses. You need to be able to explain to me in a real life example what an inverse is, how it's used, and when you're given a linear equation, you need to be able to find the equation of the inverse and also be able to graph that by switching the table of values. I hope you learned lots.